In today's class, we are going to begin with chemical equations. So, a chemical equation is a shorthand form of writing a chemical change. Okay, so let's take an example. So NH4OH, this is NH4 is ammonium, OH is hydroxide. So ammonium hydroxide reacts with HCl to give NH4Cl plus H2O. Okay, so this arrow determines that this on the left side of arrow, this was the reactant. So this was there initially, and this reactants, they react to give the products. So on the left hand side of arrow, we have the reactants, and on the right hand side of arrow we have the products. Okay, so one example is of one reactant and 2 or 3 products. Okay, this type of reaction where there is only one reactant and it forms 2 or 3 products, this is also called as decomposition reaction. We'll learn this in the next chapter, but you can just remember it from now itself. What is happening is there is a big molecule. So this molecule, big molecule, it breaks down into smaller molecules. So we call this as a decomposition reaction. Next example is of 2 reactants and 1 product. So in this case, what is happening is small molecules are coming together to form a large molecule. So this type of reaction is called a combination reaction. So for example, ammonia reacts with water to give NH4OH. So this is called a combination reaction where small molecules, they react to form a large molecule. Next is 2 reactants and 2 products. So this one can be of different types of reactions. I'll not talk about this right now. Just like this example, this is also an example where 2 reactants are reacting to form 2 products. So another example we can take is of Mg plus 2 HCl, which is a dilute, to give MgCl2 plus H2. So in this reaction, this Mg is replacing hydrogen and taking hydrogen's place. So magnesium is replacing or displacing hydrogen. This reaction is also called as displacement reaction. But remember, in 2 reactants and 2 products, there can be other different types of reactions as well. But this one, where there are 2 reactants and forms 1 product, this is a specific combination reaction. This one is a specific decomposition reaction. And the last type of reaction are 2 reactants and 3 or 4 products. K2Cr2O7 potassium chromate reacts with HCl concentrated to form 2KCl chromium chloride to CrCl3 plus 7 water molecules and 3 molecules of fluorine. So this is a reaction in which there are two reactants which react to form more than 3 or 3 products. Okay. So a chemical equation, what information do they provide? So informations provided by chemical equation. Okay. First of all, it tells us about the chemical nature of the reactants and products. Second, it tells us about the nature of elements and radicals involved. So just like if we consider this reaction, so magnesium reacts with hydrochloric acid to form MgCl2 and H2. So what we conclude from this reaction is that it tells the magnesium is more reactive as compared to hydrogen. That is why magnesium is able to displace hydrogen from its place. So we get to know the nature of elements and radicals that are involved in a reaction. The third point is the direction of the reaction. So over here what is happening is ammonium hydroxide reacts with hydrochloric acid to form ammonium chloride and water. So the direction, these are the reactants and this is the product. So direction is this, from this it's forming this. So we get to know the direction, and there are two types of signs. This one that we learned over here, this is for irreversible reaction, that once this is formed it cannot revert back. So these are irreversible reactions, and reversible reactions are denoted by this sign where it can go front as well as come back. So this is denotes reversible reactions. So the direction of the reaction can be known by the chemical equation. And also number 4, the state of matter in which substance is present that is in solid, which is denoted by S, liquid denoted by L, and gaseous denoted by G. So the state of matter is also known by a chemical equation. Now these are the informations that are provided. So what information does it lack, or the limitations of a chemical equation? First limitation is that the concentration of both reactants and products. So basically this is a limitation because suppose it's written dilute hydrochloric acid. So what is the percentage of hydrochloric acid and what is the percentage of water? How much dilute it is? It is not saying. And when it is referring to concentrated HCl, again it is not saying how much concentration is there. The exact value is unknown. So the concentration of both reactants and products, this is a limitation. The second limitation is that the speed of reaction is unknown. So how fast or how slow the reaction proceeds is also unknown. Third, changes in color occurring during a reaction. So what color the solution is formed, that is also another limitation. It's not given in a chemical equation. Number 4, completion of the reaction, that is when is the reaction complete, that is also not told by a chemical equation. And number 5th, the last one, changes in evolution of light energy or sound energy. This is also not denoted by a chemical equation. Though heat is mentioned, but light or sound energy is not mentioned during the occurrence of the reaction. So this is the last limitation. Okay. Next thing that we need to see is that, see, here we have 1 nitrogen, here 1 nitrogen, 4 hydrogen, 4 hydrogen, 4 plus 1 5 plus 1 6 hydrogen, 4 5 6 hydrogen, 1 oxygen, 1 oxygen, 1 chlorine, 1 chlorine. So this reaction is already balanced. But some reactions previously are not balanced, like this reaction. So we had to put some numbers in front of the number of molecules so that we could balance this reaction. So why do we need to balance this reaction, and what is a balanced reaction? Okay. So what is a balanced reaction? So a balanced equation is one in which the number of atoms of each element is the same on the side of reactants and on the side of products. So there is a simple reason for this one. Suppose you say that there was a nitrogen, so N2 is there. So over here, how many nitrogen is produced? Only one. How can we get only one nitrogen from two nitrogens? So that is the reason why we put these numbers in order to balance this, because the number of atoms of each element should be same on the side of the reactants and on the side of the products. And next question is, why should an equation be balanced? And a simple and scientific reason for this is the law of conservation of mass. So how much mass we had taken earlier, the mass can neither be created nor be destroyed, hence the total mass should remain same. So if each atom, the number of atoms of each element remains the same, then the mass is automatically conserved. So why should an equation be balanced? All equations must be balanced in order to comply with the law of conservation of matter, which explains that matter is neither created nor destroyed in the course of a chemical reaction. And an unbalanced equation would imply that atoms have been created or destroyed. So this is the reason why we need to balance an equation. Okay, now let's learn how to balance an equation. So balancing of chemical equations. So first method, this is called the hit and trial method. This is the method that is mentioned in your syllabus and is important. The second method is called the partial equation method, that is not mentioned in your syllabus particularly. So that may or may not come. So we are going to do this in detail and we'll also learn about partial equation method. So first method, let's take first question. Say K2Cr2O7 plus HCl and gives KCl plus CrCl3 plus H2O plus Cl2. Okay, so this is one difficult equation to balance, not a very easy one. So we'll use pencil and eraser always to balance an equation, because we are bound to make some mistakes while balancing them, so we can erase easily and again rewrite them. So first let's see potassium, 2, here 1, so we put over here 2 to balance this. Now let's come to chromium. Here we have 2 chromium, here there is only 1 on the right hand side, so we put 2 over here. Oxygen is 7. So 7 oxygen means we need to put a 7 over here. So to oxygen to become 7. In the process what we have done is hydrogen becomes 7 to 14. So hydrogen 14, we need to put 14 over here for hydrogen to become 14. So when we put 14 here, hydrogen is also 14, chlorine is also 14. So 14 chlorine, let's check over here. We have 2 chlorine here, 3 2 is a 6 chlorine here. So 2 plus 6 plus 2. So 6 plus 2, 8 plus 2, 10. We need 14. So 2 plus 6. How much more do we need? 8. So we'll put 4 over here. 4 2 is 8. 3 2, 6, 7, 8. We need 6 here. So we put 3. So 3 2, 6. 3 2, 6. 6, 6, 12 and 13, 14. So we have balanced the equation. So this is 14 here, this is 2, 2, 7 and this is 3. So we need to check each and every atom, that each and every element is balanced. So again we will check once again. Potassium 2 on the left hand side, on the right hand side potassium 2, K2. So 2 into KCl means this 2 is for K also and Cl also. So K2, Cr2, 2 into 1, chromium 2 and here 2 into 3, chlorine is 6, oxygen 7, 7 ones are oxygen 7, hydrogen is 14, 7 twos are hydrogen is also 14, chlorine we have 14, so 2 ones are 2, 3 twos are 6, 3 twos are 6. So 6 plus 6, 12 plus 2, 14. So chlorine also balanced. So this equation is now balanced. Second example. Al2O3 dot 2H2O plus NaOH gives NaAlO2 plus H2O. Okay. So 2 aluminium, we put 2 over here to make aluminium 2. In the process we have made sodium also 2. Here sodium is 1. So we put a 2 over here. So okay, aluminium 2, oxygen 3 and here 4, 5 and here 6, 7. Here oxygen 4 plus 1, 5. So okay, we will hold this for now. We'll balance oxygen a bit later. We have 4 hydrogen and 6 hydrogen. Here there is only 2 hydrogen. So we put 3 over here, 3 to the 6 hydrogen, 4 plus 2, we have 6 hydrogen. So aluminium balanced, 2, 2, hydrogen, 4 hydrogen, 4, 5, 6, here 3 to the 6, left hand side, right hand side, hydrogen balanced. Sodium 2, sodium 2 balanced. What is left is oxygen. So 3, 2 ones are 2. So 5, 2 ones are 2, 6, 7. 2 twos are 4 oxygen and 3 ones are 3. So 4 plus 3, 7 oxygen. So left hand side also 7, right hand side also 7 oxygen. So with this our equation here is balanced. Okay. The next equation, number 3. Fe2O3 plus aluminium gives Al2O3 plus Fe. I write the other equations as well. Number 4 is aluminium nitride plus H2O gives AlOH3 plus NH3. And fifth one, Cu copper plus HNO3 concentrated. This gives CuNO3 2 plus H2O plus NO2. Okay. Now let's balance this. So iron 2, we put a 2 over here, iron balanced. Oxygen 3, oxygen 3. Aluminium right hand side there is 2, left hand side there is 1. So we put a 2 over here. So with this aluminium is also balanced. So Fe2, Fe2, O3, O3, Al2, Al2. So balanced. Aluminium here 1, aluminium 1, nitrogen 1, nitrogen 1. Here hydrogen is 2, here hydrogen is 3 plus 3, 6. So we multiply with 3 over here, 3 to 6. So hydrogen, this 3 over here, remember that this is for oxygen as well as hydrogen. So oxygen is 3, hydrogen is 3. So oxygen 3, oxygen 3. So with this equation is also balanced. Now the next one, copper reacts with concentrated nitric acid to form CuNO3 2 and water and nitrogen dioxide. So here we see that copper 1 balanced, nitrogen there is 1, here 2 and here 3. Okay, so this 2 is for nitrogen and oxygen both, so 2 and 1, 3. So we put 3 here. So hydrogen with this becomes 3, but hydrogen here is 2. So what we do is we'll just increase by 1, because here hydrogen we can easily make 4, but nitrogen is distributed in 2 different molecules. So we can also make nitrogen 4. So that is easy. So we'll replace this 3 here with 4. So 4 hydrogen, we put a 2 over here, 4 hydrogen. 4 nitrogen, here we have 2 nitrogen, and if we put a 2 over here, nitrogen also becomes 2 plus 2, 4. So the 4 nitrogen, 4 hydrogen, copper balanced, only oxygen is left. So 4 into 3 is 12 oxygen is there on the left hand side. 3 2s are 6, 2 1s are 2, 6 plus 2, 8, 2 2s are 4, 8 plus 4, we have 12. So oxygen with this is balanced, and with this we complete our hit and trial method for balancing equations. Okay. So next is balancing of chemical equations This is the second method. This is called the partial equation method. Okay. First example, a reaction of Ki and H2O2. So this takes place in steps. So first steps is the breaking down of H2O2. H2O2 breaks down to form H2O plus 1. This is called a nascent oxygen. So nascent oxygen is reached, one molecule of. In the second part, what happens is now this potassium iodide, this reacts with the water that is produced and the nascent oxygen to produce KOH, 2KOH and I2. So this water that was produced was used here, so this cancels off. This oxygen produced has been used, so cancels out. So overall reaction, what happens is Ki reacts with, we had 2K, so 2K, 2I, 2I, 2H, 2H, O2, O2. So this was balanced. So Ki plus H2O2 reacts, and right hand side we are getting, so those cancelled out, so we have 2KOH plus I2. Okay. So this is our final reaction. The second example is of reaction, or basically oxidation of H2S by KMN, potassium permanganate, KMnO4. So first part, what happens is the KMnO4, this reacts with, here we are taking KMnO4, that is acidified. Acidified means it has some acid, say H2SO4. So potassium permanganate reacts with H2SO4 to produce K2SO4, 2MnSO4 plus 3H2O and 5 nascent oxygen. So I am balancing this. here we have 2. So with this, yes, this is balanced. And in the second part of the reaction, what happens is, so this gave nascent oxygen. So nascent oxygen is basically responsible for oxidation. So H2S now reacts with nascent oxygen to give water, and sulfur is reduced. So here we had 5 nascent oxygen, but here we are using only 1. So what we'll do is we'll multiply this whole equation by 5. So each and every we are multiplying by 5, because this 5 nascent oxygen will be used by 5 hydrogen sulfide to form 5 molecules of water and 5 sulfur. So 5 molecules of nascent oxygen and 5 molecules of now this nascent oxygen on the product side and the reactant side, they cancel off, and we get 2 KMnO4 plus 3 H2SO4 reacts with 5 H2S to give K2SO4 plus 2 MnSO4 plus 3 molecules of water and 5 molecules of water, that is 8 molecules of water and 5 S. So this is our final reaction. So this is how we solve our partial equation method. Now we come to the final topic of the chapter, that is the relative atomic mass. And relative molecular mass. So what happens is, atoms are extremely small. They are not even visible by our naked eyes. So atoms are so small, they are extremely small and very light, and hence they cannot be weighed directly. We cannot weigh one atom. So what we do is we use indirect method to determine the absolute mass of an atom. Now this indirect method basically involves relating the mass of one atom to some other atom. So initially what happened is, we took the hydrogen atom as the standard unit and we measured all the atoms according to hydrogen atom, but later on it was switched to carbon. Okay, so atoms are extremely small and very light, and hence they cannot be weighed directly. So indirect methods have been utilized to determine the absolute mass of an atom. So this indirect method is basically the relative mass of an atom. So therefore the relative mass of an atom is considered by considering a mass of a light atom and relating the mass of other atoms and molecules to it. Okay, this one I have written particularly because you can be asked why relative mass of an atom is considered instead of taking the weight of the atoms directly. So this is your reason, because atoms are extremely small and very light, they cannot be weighed directly. So we use indirect method like taking the relative mass of an atom and we consider a mass of a very light atom and relate the mass of other atoms to that. Now initially what we took into consideration for taking the relative atom was hydrogen. So hydrogen atom being the lightest element was initially chosen as the standard unit and masses of other atoms or molecules were compared to it. But later it was discarded because the comparison by hydrogen atom did not give very accurate results. So later on what we took was carbon isotope of C12. So carbon 12 atom, an isotope of carbon was later in 1961 considered the standard unit for comparison of mass of other atoms or molecules. Okay, so now we will define relative atomic mass and relative molecular mass. Relative atomic mass. So why relative is because we relate it to carbon. So this is also said as RAM. So atomic mass, RAM, relative atomic mass, or we also call this as atomic weight. Of an element is the number of times one atom of an element is heavier than, okay, see now mass of this carbon is approximately 12. So to take it as a standard unit, we take 1 by 12 of this 12. So 1 by 12 of 12 is basically 1 unit. So heavier than 1 by 12 the mass of an atom of carbon. C2H. So relative atomic mass is basically equals to mass of one atom of the element divided by 1/12th the mass of one atom of carbon C2H. So with this we also learn gram atomic mass, also called as a gram atom. So this is the relative atomic mass since we are saying gram atomic mass, so means the unit basically becomes gram. So the relative atomic mass of an element expressed in grams is known as gram atomic mass or gram atom of that element. Now, the relative molecular mass or RMM. So the only difference between relative atomic mass and relative molecular mass is that here we are taking relative atomic mass. Instead of relative atomic mass we will write relative molecular mass. That is the molecular weight of an element is the number of times one instead of atom will have molecule of the substance is heavier than 1/12 the mass of atom of carbon C2H. So the definition is going to remain the same. Wherever we have atomic, that will be replaced with molecular, and that is it. The definitions are basically same. So replace. I'm not writing the definition. You can just learn this and replace atomic with molecular. It's that simple. Replace atomic by molecular, and wherever it's written RAM, replace by RMM. That's it. That's the only difference between the two definitions. And gram molecular mass or gram atom, gram molecule so this becomes the relative molecular mass of a substance expressed in grams is known as gram molecular mass. Okay. So over here, so this gram atomic mass or gram molecular mass, the unit is gram. So what will be the unit for relative atomic mass or relative molecular mass? So atomic weights are expressed in atomic mass units, that is AMU. What is an atomic mass unit? One atomic mass unit is defined as one-twelfth the mass of a carbon atom C12. So this is our atomic mass unit. Now, a very important give reason. The mass that we take for chlorine is 35.5, but the mass number, there are two isotopes of chlorine, one is of 35 and one is of 37. So why do we take 35.5? Okay. The atomic mass or the atomic weight is the weighted average of the atomic weight of its natural isotopes. So we are taking the average. Chlorine exists in two isotopes, Cl1735 and Cl1737, in the ratio 3:1. So therefore, average atomic weight will be equals to 35. There are 3 in the ratio, so 35 into 3 plus 37 is 1. So 37 is 1 by 3 plus 1, the total. So this becomes 105 plus 37 by 4. So that is 2. 7 plus 5, 12, 142 by 4. So 71 by 2, that is 35.5. That is why we take the average atomic weight of chlorine as 35.5 AMU. So this is one important give reason that you may get. Okay, now some very basic question relating this molecular weight and percentage composition. So I'll solve one question each. So calculate the relative molecular mass of ammonium sulfate. Ammonium sulfate is basically NH4 to SO4. Okay. So in the question you might be given the atomic weight of individual of them, but make sure you learn them as well. We have already discussed the mass numbers of each of them in the chapter atomic structure. It is the same. Only for chlorine we learned there 35. That is going to be 35.5 because of the average atomic weight. Others it's going to be the same. So solution. So molecular weight or relative molecular mass is the same thing. So molecular weight of NH4 to SO4 will be equals to, see, NH4, nitrogen is 14 plus hydrogen 1, and there are 4 hydrogen molecules, so into 4, and this whole there are 2 of them present, so into 2, plus sulfur is 32 plus oxygen is 16 into 4. So this becomes equals to 14 plus 4, 18 into 2 plus 32 plus 16 4s are 64. So 18 to 36 plus 6, 96, 6 6 12, 3 to 12 plus 1 13. So that is 132. We can write AMU. If you do not write AMU, that is also fine, but do not give gram. This is relative molecular mass. When the question asks for gram molecular mass, that time you will write the unit as gram. Else if you write it as gram, then it will be completely wrong. So do not put gram unless the question says specifically to find the gram molecular mass. Okay. The next example is to calculate the percentage composition of carbon dioxide, that is CO2. So solution, first what we will do is we will find the molecular weight of CO2, that will be equals to carbon is 12 plus oxygen is 16 into 2, so 12 plus 32, that is 44. So molecular weight of carbon dioxide is 44. So percentage carbon will be equals to basically the mass of carbon by the molecular weight of CO2 into 100%. So mass of carbon we have 12 by 44 into 100%. I am directly writing the answer over here. This will come out to be 27.27%. You can calculate to reassure if it's correct or not. And percentage oxygen will be equals to mass of oxygen by molecular weight of CO2 into 100%. So oxygen, there are 2 atoms of oxygen present in one molecule. So one oxygen is 16, and since 2 are present, so 16 into 2 by, we have 44, the molecular weight of CO2 into 100%. So this on calculation we will get 72.73%. So this is how we find the percentage composition. So if you are asked for say NaOH for example, so you will find for sodium separately, for oxygen separately, and for hydrogen separately. You need to find each one of them separately. So this is how we solve questions for percentage composition. With this we come to the end of this lecture. Thank you.